I'm Christian Lewe from Blockstream Research. This is going to be more theoretical. It's going to be a talk about how we use Nix in our research at Blockstream Research. So it's called Simplicity plus Nix equals Love, which I think is a good title. I came up with the title, and then I had to come up with the content, which was the hard part. All right, so what do we do? What do I do? What do we do at Blockstream Research? At Blockstream Research, we do cutting-edge Bitcoin research, as the name implies. In particular, we work on Simplicity, which is a universal smart contract language for Bitcoin and for Liquid that Russell O'Connor, who was mentioned here before, came up with, created, and has maintained. He has maintained this for almost 10 years now. So it's a pretty old project, which is still growing and which is still not obsolete, which is a good thing. Like I said, it has universal smart contracting capabilities. So with this, you can enable all conceivable smart contracts that we want on Bitcoin. And it uses a verifiable software toolchain. So it's written in so-called verifiable C, and it has a formal specification. So we can make sure that what we write is actually correct according to our specification. And we are working on a Liquid integration right now. And this is going to be the next big step. And then after that, we will focus more on Bitcoin itself. So that's what we do. That's what we do in 4 bullet points. I'll talk about first how our project Simplicity benefits from Nix. And then after that, I will talk about how Simplicity lends itself to the Nix infrastructure, how Simplicity works particularly well for Nix. So Simplicity is a pretty complex project. So we have at least 4 code bases. We have C, we have Rust, we have Haskell, and we have Coq. This is the thanks to the French for this name. And so this is the formal verification part. It's the Coq theorem prover allows us to formally verify our code. So the specifications are written in Coq, and then we can connect this, check this against the C code, which is the consensus relevant code base. So all these code bases fulfill certain roles, and we have to build them, we have to test them, we have to maintain them. It's pretty complicated, and separate people work on these projects, so that's complexity. We also use vendoring. So this means, for instance, there is C code which is copied to the Rust crate for FFI, for a foreign function interface. There also is Haskell code which generates C code, and there is Haskell code that generates Rust code, so additional complexity. We run elements D. So this is the elements is the open source component of Liquid, and elements D is the bitcoinedev for Liquid, basically. And we use a patched version which runs Simplicity. And if you have ever compiled bitcoinedev or elements D, you know this is not an easy feat, especially if it's a patched version. So making sure this all works is complicated. And then we also have a tech report, which is not always up to date. It's written in TextMax, which is the weirdest LaTeX format I know. And honestly, I could not build it without Nix. So after Russell graciously wrote a config, I was finally able to build this locally, which is really useful. We also have a complex CI, so we want to test all of this, that what we write works. So we have a minimum supported Rust version for our Rust crates. And so this means that we can compile our Rust crates with this minimum supported Rust version. So it doesn't compile only with the latest version, but also with this previous version. I think right now, I don't know, we increased it recently. I think it might be 1.58 or something. So it's not 1.70, it's 1.58 or something. So it's a few years ago. And making sure this works is, so this is not a feature that is really supported by Cargo, which is the building tool for Rust. So making sure this works is also complicated. Again, the vendoring, so if someone updates the vendored code, we have to make sure someone copied the right code. And because every time we copy something, there's a potential for malware. We run fuzzers, so we test our code against random inputs that are created by the fuzzer, and the fuzzer tries to make our program crash. And if it fails, then we conclude our program is pretty good. So this must work, and also anything that uses Bitcoin nodes or elements nodes and complicated tests, we need to make sure they run in the same way on all computers. So if the bugs need to be reproducible, if there's any bug, anything that uses more than one node is a complex scenario that we need to somehow encapsulate in a configuration file, and somehow we need to be able to run this multiple times in the same way. And also our team is complex, so we are on different continents. We run different computers, different architectures, different operating systems. The software must just work. So if I have a bug in Europe on my NixOS, whatever, on this laptop, then Russell O'Connor in Canada must be able to reproduce this bug, or Andrew Polstra. We live in different countries, and we cannot just go to each other and help each other out if there's a bug. Right, so this is really important that the software works. How Nix helps? Nix makes sure that our dependencies are complete, so we actually have to think about what is required to make our tests or our binaries work. How can we compile them? How can we run them? Because if we don't specify something, if we forget something, there will be an error for us as well, right? So it cannot happen that we install something on our local system, forget about it, everything works, and then we ship the software, and then our colleague or even the customer, they run it, and they don't have the dependency, and then there's a bug. This, with Nix, the error is on your computer, on the developer's computer, and you can catch it and you can fix it. We have one-liner installations. I will show you something in a minute. So running these tests, building these binaries are just one-liners, even though we run really complicated software. So this is, like I said, it's cutting-edge research, and which means it's complicated software, multiple code bases, and still we can run it in one-liners, which is amazing. We can reproduce our builds, and most importantly, we can reproduce bugs. So if there's a bug, there's always some kind of bug, we can reproduce it, and we can put this in a PR or on a messenger somewhere, and we can try to fix it. I want to show you a particularly bad example. It's a good example, but it shows you how bad it is to not use Nix. So if you want to do the formal verification, you can do that. So you can go to our simplicity repo. Will be a link later, and you can run this command. And this will build the formally the COC code, which is a list of definitions of theorems, and it will execute the proofs, which will basically say the simplicity is well defined, and the runtime has certain properties and so on, and the programs have certain properties. And if you run all of this, you have basically formally verified simplicity on your local machine with one command. Sure, it will take some time, but it's just one command. Let's do this manually, just setting it up, right? So just setting it up. First of all, you have to install the OPIM package manager, because this is this OCaml. So this is this really weird package manager. You have to install it. I don't even have the installation here. You have to initialize it. You have to set up your shell for it. Then you have to install COC, but you have to install a specific version, 8.15. Don't install the latest version, MadBreak. And then you have to install a patched version of the verified software toolchain from Princeton University. So the verified software toolchain enables us to formally verify C code and the simplicity C code, and also, as far as I know, libsecp is written in this specific verifiable C style, which is a subset of C, and you can write theorems about it. So there's a formal COC equivalent to each program, to each C program, and we can we can prove that the program is correct, that it meets a certain specification. But because we are special in simplicity, we have to install patches. So we have to do something, some SHA business, some hash business, custom SHA implementations. I don't know what this does, but it's complicated. And this, you might need to configure it. So you have to actually know what these programs, what these lines do. I don't. And then you have to go to the coq the directory. You have to execute the coq makefile, which creates a makefile, and then you have to execute the makefile, double make. And then after this, I think you have verified simplicity. Okay, so this is one line, and this is more than one line. So I recommend you do the one-liner because there's less potential for error. And you find all of these lines in our repository as well. Okay. So the takeaways are, you can run the latest Bitcoin research on your machine with Nix, and it will just work. The results that we have are reproducible, so if it runs on our machine, it also runs on your machine, and it just speeds up our development. So without Nix, we could not develop at this speed. With a small team that works on simplicity, and without Nix, everything would just be slower. So thanks, Nix. This is part one, the main part. And then I was thinking simplicity is also very, well, let's say amenable to Nix, or it's like it works well for Nix because it's a functional language. So let's take a look at that. Why does it work for our project, and how can you know that it works well, that Nix could work for your project especially well? How can you change your project to make it work better with Nix? There are a couple of points that make Nix better, or that make this workflow better. So a functional language like simplicity or functional programs work really well. A functional program means, among other things, that this program always returns the same outputs if you give it the same inputs. So it's deterministic. It runs, so in this case, it's a simplicity program or the simplicity interpreter. It runs in an isolated runtime. So we know exactly what the runtime consists of, what the parameters are for a simplicity program. And then inside that environment, the simplicity program always runs in the same way, and always the same way. If there's a bug, there will always be the same bug. If there's no bug, there will always be no bug. We can verify the outputs, we can verify the inputs. All the side effects are well defined. A side effect is when the program like modifies the outside world, outside of the environment. So maybe a file is written, or a file is read, or something that is in the outside world. And simplicity actually almost never has, like, it almost does no side effects. Like, the only side effect it does is the programs might fail. Like, there might be an assertion in the program that fails. So like a signature check can fail. That's a side effect. Or it runs it reads from the current transaction. So it reads a signature hash from the transaction. That's also a side effect. That's a side effect that simplicity can have. If your program, your project has more side effect, if it like reads crazy things from the network or from the file system, then obviously it will not work as well with Nix, because all of this is impure, and if the outside world is different, if the things you read or write fail or are different, then the outcome will also be different. And like I said, simplicity is verifiable, so this just means that the points above actually are true. So we actually verify that simplicity is deterministic, has an isolated runtime, and has well-defined side effects. And also the runtime is small, so simplicity, the name kind of comes from the fact that simplicity is the smallest set of features you need to do what it does, and what it does is universal smart contracting on Bitcoin. So it's not nothing, but it's very little code for what it does. And little code means small attack surface, few things that can go wrong. And like I said, it's also verified. So the probability that we have a bug is relatively low. It also means that we can write exhaustive tests because the number of possibilities is so low. For instance, we have 9 combinators, so 9 basic functions that simplicity consists of. We can test these 9 things. With Bitcoin script, I don't know if someone knows the number, I don't, but we have many more opcodes, maybe 50, maybe 100 opcodes. Just testing 100 takes much longer than testing 9. And if you test if you do combinations of opcodes, then this it explodes, whereas with 9, that's much simpler. You also have few dependencies, so again, fewer things that can go wrong. So simplicity is minimal, and if there's a small code base, then Nix has an easier job making sure that everything runs and the configuration files are short and so on. And the formal verification is one of the main selling points of simplicity. So what we can do is we can write a formal specification for the runtime and also for a program and specify what does the runtime need to do, what is the execution, what is a correct execution. And then if I write a program, I want to realize a certain spending condition, and I can formally verify that the spending condition is correctly encoded in the program. And then it runs on the correct runtime, so it actually works. So yeah, correct runtime, correct programs. We can even, and this is obviously a lot of work, but it's a lot of work, but the runtime for sure, the runtime runs all the programs, which means it manages millions or billions of dollars worth of Bitcoin. So making sure this works is worth it in my estimation. And then for the programs, you need to formally verify each program if you want. This is a lot of work, but again, the programs are often reused. So for instance, a Lightning HTLC is reused. If we verify it once, then we have the benefit every time we use it, and we only have the cost once. And then we have the guarantees that formal verification gives us. And we could go further. This is like far future stuff, but we could even, so imagine simplicity is somehow merged or it's used, and we want to make sure we don't break it. So it's correct, but we don't want to break it. Every time we make a commit or PR, we could write a formal proof that the commit is correct or doesn't break the correctness. Sorry. And we can run the proofs locally, and running the proofs locally means you need a setup. And this means Nix is pretty good, because Nix enables you to just execute all of this in one line instead of doing this long stuff that I showed you, because you need to do this long stuff to do the stuff on the slide. Okay? So really, the true power of formal verification comes from the fact that everybody can run it with a minimum setup, with like a really easy setup with a one-line setup. So the takeaways are, if your project is like functional, so if it is well-defined what it reads and what it needs, if it's deterministic, then it lends itself to Nix. Then Nix, which is also functional and pure, will work really well with it. Otherwise, the two will kind of battle each other. Less code can be better tested. So if the goal is to make sure to have correct software, having like a small code base is obviously good. And a small code base also means, like I said, a shorter configuration file and fewer things that can go wrong. Verified code has fewer bugs, so if we can verify our code, we will find bugs, and there will be bugs. Whereas if after the verification, it's a very low chance that we find bugs. And then we have the benefits of Nix, which makes sure that the deployment is really easy, and we actually deploy correct code, which is good. So it's easy to set up, and it runs correctly. You find our research on GitHub. So we also have blog posts and so on. I felt I just put the GitHub link. So you find the simplicity repo, the Rust simplicity repo, other kinds of repos. So you can check this out, github.com/blockstreamresearch. And that's it. Thank you for your time. Happy to take questions.
Just a quick comment. I think why the both work so well together is that you already need some gigabrains to understand simplicity. So if you already have them, then why not do it all in Nix?
Yeah, maybe I should have Russell O'Connor on your team. Makes it much easier to deploy Nix, yeah. Apparently he was the person who introduced Blockstream to Nix, so that helps, yeah. Or having at least someone like write the configuration once, make sure it works, and then it works for everybody, right? So if you find a glitch in simplicity, I mean, there are different code bases, right? So you can open an issue. I'm sure, I will definitely make sure that we will have a bounty program once it's like properly deployed, because if anybody has a bounty program, it should be us. Like we are saying formal verification, complete absence of bugs. So we should have a bounty program. We don't have that right now. There are certain code bases that are not consensus critical. So the only critical is the C and the COG. And for instance, the Rust and the Haskell code bases are much more malleable, and there could be more bugs. But if you have anything for now, it would be amazing if you could open an issue. Or hold on to it until we have the bounty program. Yeah, that could work.
Hold on to it until it's deployed.
Sure. So is there a GitHub that's publicly accessible yet for Simplicity's code base?
Yes, for Simplicity's database?
Or its code base.
Yes, there is.
So bugs could be reported through GitHub's bug tracking system for now.
Yeah, so it's on GitHub. It's here, Blockstream Research / simplicity. And as you can see, there are some issues. So you can report it here. For instance, the stop code needs to be updated. That's the C, Haskell, and COG code base. They're all in the same repo, and the Rust code base lives in Rust simplicity.
Cool. Thanks, Chris.